we have Jack, who's going to talk about the horrible Planar Continua.
Thanks for the introduction, Willie. So it's nice to see everybody. I only have a couple people in my floating meeting control here, but yeah, that's great. So I hope everyone's doing well. I kind of want to talk about horrible planar continua, just horrible compact connected sets, what could happen. So it's kind of going to be like a topology vibe. And normally when we construct really bad examples, like in Top Geo1, you have to make some like T2.5 space that's not T3.5 or something like this. It kind of seems very pointless, but some of these things do show up when you're doing complex analysis and complex dynamics. So that's where most of my research takes place. So I kind of just wanted to show you, some of the awful things that us, people that do dynamical systems on the large and people who do analysis, we have to keep these sorts of things in the back of our mind because they show up in things like partial differential equations, stable or unstable sets for dynamical systems. So I also hope it's a little bit fun along the way. So without further ado, so I have some fun objects here. So this is a Julia set that shows up in complex dynamics. We'll talk a little bit about here. This, believe it or not, is a Jordon curve, the smiley face, if you can all see my cursor. It's a little bit difficult to decide if you're in the inside or the outside of the Jordon curve. So we'll talk a little bit about that later. And then maybe we'll talk a little bit about bucket handles and pseudo-arcs, but I'm not sure we'll have the time to do that. So without further ado, let's try to maybe establish some common vocabulary that we should all be sharing in this talk. And that's just what a curve is. And so I think this definition is very pleasing. So a curve in a metric space X, so this works in any general metric space, it's just a continuous function gamma, which maps the unit interval onto the metric space. So most of the time for us in this talk, it's just going to be some subset of C. So anything that's the continuous image of the unit interval, we're going to call a curve. So it's very general. And then we'll also just use some other vocabulary. I'll be spitting this out the whole time. So we'll have closed curves. So by a closed curve, I mean that gamma 0 equals gamma 1. Its start point and its end point are the same. And then, of course, we have things like simple curves. So that's curves who don't cross itself. So we have, if t is not equal to s, then we want gamma t to not equal gamma s. So of course, something that's not really a curve is something, like our bow tie or something like this. It crosses itself. So anything that doesn't do this, I will just call simple. And if my curve is simple and closed, so I allow the only time where the curve is allowed to equal itself to be on the endpoints, I'm going to call it a Jordon curve. And so this is going to be a word I use a lot. But yeah, a Jordon curve is just going to be a simple closed curve in the plane. And, that's things like circles. Well, that's not a circle. I didn't close it up. Any sort of wiggly, sort of blobby type domain, that's going to be a Jordon curve right here. And that's probably going to be our main object of study in this talk. Just, what do Jordon curves really look like? So simple closed curve is a Jordon curve. And then some other vocabulary that I'll be using, I'll call an arc. So, arcs and curves, they're not really different. But when I think of an arc, I think of something that sort of has a distinct start point and end point. It doesn't necessarily go back to itself. So when I say arc, I'm going to always mean a curve, but it's never closed. Its endpoints are always going to be distinct. So that's what I'll refer to with an arc. And then an important word is the notion of when a curve is rectifiable, a rectifiable curve or arc. And I don't really want to mean anything in sort of like scary geometric measure theory terms. A rectifiable arc is just going to be a curve. It's just going to be a curve who has finite length. And we know how to figure out what the length of a curve is from a calculus class or even a real analysis class. The length of a curve, what you do is you just sort of split your curve up into little pieces, and then you measure the distance of all the line segments that's sort of like determined by the mesh right here. And then you choose the supremum of all of these quantities. And so that's what the length is. So you take the sup, you break up your unit interval, and you look at the distance between all of the image points. And that's going to tell you what its length is all the time. So I hope that this definition is standard right here. But a rectifiable arc, it's always going to satisfy that this quantity is finite. So we'll use all of these words at some point, but we have all sorts of conditions on our very simple definition of a curve. And like I said before, we'll be interested in curves that are a subset of R2. So maybe we can ask ourselves a question. What are curves? Is there a possible way to characterize curves maybe in just a simple topological way? And there actually is a way to do this. And so this is an old theorem of Hahn and Matrikevich. And it says that a non-empty Hausdorff topological space X is the continuous image of the unit interval. So that means it's sort of the image of the curve. This is actually kind of an important subtlety, and I'm going to go all the way back up actually. So a curve is actually the continuous function. So that's how it's always defined. And then its image is sometimes called the trace. So image of gamma is the trace. So that's sort of like the geometric object that we view inside of our head. And I'll be referring to these interchangeably if I'll like look at the trace of a curve, and I'm just going to call it a curve. But whenever I say that something is a curve, we should always kind of keep in the back of our minds is, oh, this is a continuous function that actually maps onto this geometric object that I'm visualizing right there. So I'm going to not be careful with that through the rest of the talk, but it's one subtlety that I did want to mention. Anyway, it's the theorem of Hahn and Matrikevich that a non-empty Hausdorff topological space, it's the continuous image of the unit interval. So it's a curve. It has some parameterization. That's another way to refer to that. If and only if the following three conditions are satisfied. We need the space to be compact. We need the space to be connected. And we need the space to be locally connected. So if I have any subset of R2 that's compact, connected, and locally connected, I can realize it as the continuous image of the unit interval. It is the trace of some curve. So we can call that object a curve actually. It's pretty easy to see that all of these conditions are necessary, right? Because a curve is going to be the continuous image of a compact set. So obviously it has to be compact, and it's the image of a connected set. So obviously it has to be connected as well. And then we also have this silly notion, well, it's not silly actually, we kind of have the more annoying notion of local connectivity. But if you have a uniformly continuous function, like, you know, a continuous function on a compact set, then its image is always going to be a locally connected set. And a locally connected set, just to remind everyone, means that you take every point and it has a neighborhood basis of open connected sets. And the example I always keep in mind of something that's not locally connected is this topologist sign, is this like a topologist comb right here. So you just kind of draw an interval, and then you draw teeth of a comb that are going to slowly start to accumulate, say at like pace 1/n on like the cone that's going, the what do I want to say? The vertical piece that's going vertical at the point 0, 0 right here. And so you'll be able to see that if you choose any point on this little segment that I've attached to my comb right here, well, all of the segments to the right, all the vertical segments to the right are accumulated on this comb. So when I give it the subspace topology, I cannot give this point a neighborhood basis of connected sets because it's always going to see one of the combs a little bit to the right. So this is not a locally connected set. And like I said, if you have a locally connected set and you apply a uniformly continuous function to it, its image is always going to be locally connected. That's actually a somewhat annoying exercise to prove. I remember spending a long time doing it a few years ago, and I never want to do it again. I'm pretty sure I've forgotten how to do it actually. But it's just three really simple necessary conditions that a curve must satisfy, at least its image. And it turns out that these are all sufficient. If you give me any space that's compact, connected, and locally connected, I can parameterize it. So this includes things like space filling curves, because for example, if I take the unit square and I fill it in, you know, you take the closure of any open set. Well, I shouldn't actually say that, but you take a closure of any reasonable open set right here, and it says that, well, I can see the square as the continuous image of the unit line segment. You can take things like horrible dendrites that show up as Julia sets of polynomials, all these horrible fractal spaces, but they're often compact, connected, and locally connected. And so you can always give them the structure of a curve. So this theorem is very general right here. And it just shows you, how broad the class of curves really are. I always think it's an impressive one. And it's something that we actually don't really see in a topology geometry 1 course, but it's a really elegant topological characterization of continuous images of the unit interval. Yeah, that's all I have to say about curves to start off, but are there any questions so far? All right. If that's the case, and if you have any questions, just please interrupt me instead of like using the chat or something. I think this is an informal seminar anyways.
Wait, Jack, what was the assumptions on your space that you're mapping into?
Yeah, I guess I wasn't too careful about this, but if I map into, it's any metric space, I think will satisfy non-empty metric space, Paul. I guess I have to be careful there when we're doing topology. But yeah, if it's mapping onto a Hausdorff topological space like a metric space, I don't really think of anything worse than metric spaces, to be honest. So I think it would work in this sort of setting. But most of my metric spaces that I consider are just subsets of the plane given the subspace topology. Now that I haven't said the subspace topology in forever, but when you give a talk on topology, that's what you do. Are there any other questions? All right. So let's talk about the Jordon curve theorem. And I think this is a theorem that we've all heard and we've never actually proved. And I'm unfortunately not going to prove it for you, but maybe I'll tell you where you can find a proof. But the Jordon curve theorem says that Jordon curves, which are simple closed curves, just like this, are topologically simple objects. And so here's the statement of the Jordon curve theorem that I know. And so the Jordon curve theorem only works in the plane. So if you let gamma be a Jordon curve, so like I've said before, it's the image of the unit interval. So if you let gamma be a Jordon curve in the plane, then its complement decomposes into two open sets, omega in and omega out. It has an interior complementary component and an outside complementary component. Maybe I should call it X or something like this. So omega in is the bounded complementary components of my Jordon curve, and omega out is the unbounded complementary component. So any Jordon curve, it decomposes the plane into two disjoint open sets. Oh, I should actually include this hypothesis in here. Omega in intersect omega out, their intersection is equal to the empty set. So that's also a key piece. So it decomposes the plane into two disjoint open sets. Moreover, they share the same boundary. So the interior complementary component, gamma is its boundary, and so is the exterior complementary component. So all of these sorts of pieces are important things to keep in mind when we have the Jordon curve theorem. So for example, something that's not a Jordon curve, if I take a circle and I include a slit inside of it, this is sort of where the boundary condition comes in. But it has an interior complementary component, which I'll shade quickly in orange right here. And it has an exterior complementary component, which I'll shade in green outside of here. Now you'll notice that this whole curve right here, it's not a Jordon curve, so I'm not going to call it gamma. The whole curve is the boundary of the interior orange region. But the exterior green region, it does not see the little slit inside of there. So this part of the theorem is actually extremely important, that they actually share exactly the same boundary. Every point on the Jordon curve is on the boundary of both of the domains that it determines. So that's our friend, the Jordon curve theorem. And like I said, this means that Jordon curves are really topologically simple objects. And it's one of the simplest cases possible, but I'm sure we've seen lots of pictures where Jordon curves can be really geometrically exotic objects. So for example, right here, we have a von Koch snowflake. So if you ever study dynamics or complex analysis, you will eventually see von Koch snowflakes. They're everywhere, and they're somehow one of the most reasonable fractal objects to study. But basically, you just start with a triangle right here, and then you add triangles on all the midpoints, and you add triangles to all of those midpoints, and you continually add triangles, and you're going to get some fractal space that's going to be the boundary of the limit of all of these regions. And you can give it the parameterization of a Jordon curve as well. But it's a kind of horrible fractal object. It doesn't look, it's completely not smooth. If you zoom in, it's going to look jaggedy at all scales. So Jordon curves by no means have to have good geometry at all. And even though they give a bounded and unbounded complementary component region, it's not really easy to tell looking at any picture. So artists like making artwork about this type of thing. And so this is something I scooped online. But even though Jordon curves, there is an interior complementary component and an exterior complementary component. If I just choose a point right here, I have no good guess for if I'm in the interior complementary components or the exterior complementary component. So maybe this picture should convince you that it's rather impressive that you can detect that there are exactly two complementary components. Because if you kind of swim in this picture, at least on this scale, it's not super clear. So Jordon curves can be awful, and I'm going to show you more awful Jordon curves that are not just artwork, but really have like pretty awful mathematical properties as we go through the talk. And I know there's a proof of the Jordon curve theorem when you take like a course in algebraic topology, like you compute some homology group and you're like, oh, great, you know, now I know everything. But of course, you don't actually see anything when you do the homology. So sometimes people offer a really down to earth proof of the Jordon curve theorem. And this will actually work for polygonal Jordon curves who are just, you know, pieces of line segments that you glue together, like this object right here. And it's an algorithm. So I want to maybe give you this proof right here and omit several crucial details. So I have a polygonal Jordon curve gamma right here. And that means it's going to be some bounded set. It's some compact set in the plane. So that means it's contained in some square. All right. And so what I'm going to do is I'm just going to pick some base point x. So because my set is bounded and I can bound it in some square, it's made out of finitely many line segments. I could calculate, you know, what square it's contained inside of. I can choose a point that's clearly in the exterior, which is clearly outside of the Jordon curve. So then what I'll do is I will just take a line segment like so, and I'll choose some line segment so that I eventually cross the Jordon curve exactly once. And then I'll just go a little bit further. And then I have a point y right in here. So what I'm going to say is that x is it's going to be in omega out. It's going to be in the outside complementary component. And then I'm going to say that y is just going to be in the inside complementary component because I've crossed the curve exactly once. So once you cross the curve, you sort of go from one component to the other component. For all other points, z, so I can choose some sort of z right here. I'll just connect z to y. Connect z to y or x. So we can do both of these. So I have my z right here, and then I'll connect it to y via a unit line segment, like so. So it crosses the polygonal Jordon curve several times, but we can count the crossings. All right. So right here, I have one crossing, two crossing, three crossings. Brilliant stuff. So if the number of crossings is odd, then z is in the interior complementary component. Oh, wait, no, I want it to be in the exterior complementary component. Sorry, because if you cross once, then you're going to be in the exterior complementary component. So z is going to be in omega out right here. And if even, then z is going to be in omega in. So for example, if I choose another point right here, I cross once, I go in, and then I go out. So believe it or not, this algorithm actually works for polygonal Jordon curves, and I can actually dress this up to be a proof. And it's an algorithm. It's something that you could really ask a computer to do for a polygonal Jordon curve. You take any 2 points, you just decide this one has to be in the inside, this one has to be in the outside, and then you can just connect everything with line segments, and you can compute the interior, you can compute the exterior, and once you know this, then you can detect the boundary, and you have an interior complementary component, an exterior complementary component, and they all share the same boundary, and they're all going to be disjoint. So this proof works for polygonal Jordon curves, but kind of the driving question of this talk is, can I make this proof work in general? So I want you guys to think about why this would not work for a general Jordon curve. What is probably the most suspect feature of the proof? And maybe I'll allow maybe a second for everyone to compose themselves, take a little mental break, but does anyone have any guesses for what the most suspect part of this proof is that would prevent me from going from polygonal Jordon curves to general Jordon curves?
Could you have infinitely many crossings?
You can, Sam, and that's going to be something that we're eventually going to go to. It is possible that you have infinitely many crossings with a line segment, but then it's not so clear. Well, okay, so maybe I have a Jordon curve with infinitely many crossings if such a thing exists in the first place, but maybe you could just take a simple detour or something like that and then count the crossings there. I want to convince you that this argument completely fails in a very dramatic way. with a theorem I recently proved later on. But yeah, that's going to be the thing that we want to keep in mind. With polygonal things, it's pretty clear when we cross a line segment, like we can define this very carefully. But general Jordon curves, we're going to see that they're so horrible. I'm going to convince you that this is maybe not something that you should count on being able to do, given a general Jordon curve. All right, are there any questions so far? All right, let's talk about Cantor sets. I said I was going to talk about, these connected Jordon curves, and now I'm going to talk about Cantor sets, which are totally disconnected, but I'm going to make the relationship clear soon. So we're going to consider Cantor sets in the plane, and I want to describe what the four-corner Cantor set is to everyone. So this is probably, the model Cantor set space that I always keep in my head. Just like the model fractal space is the von Koch snowflake, the model Cantor set I always keep in mind is a four-corner Cantor set. So what you want to do is you want to start out with a unit square, and you want it to be 0, 1 cross 0, 1. So I can't get OneNote to actually fill my shapes in, which is horrible. So it is the filled in square. Like so. It's a really horrible feature of OneNote. I really don't understand why Paint can do it, but OneNote can't. But maybe I'll send my complaints to them instead of whining to you guys about it. So how am I going to construct my Cantor set? Well, what we do in the case of the middle thirds Cantor set is we start with our unit line segment, and then we just start taking out pieces of it. And then we take out more pieces and more pieces, and then we have some, nested sequence of compact sets, and it's going to be non-empty in its limit. So what I'm going to do is I'm going to take out this sort of plus sign in the middle right here. And so if I do that, I'm going to be left with 4 squares in K2, like so. And I have successfully removed the region, which I'm just going to color in green right here. All right, so you just take out a middle plus sign in your unit square. So that's going to be K2. This is analogous to taking out the middle interval. So now I'm left with 4 squares, and I'm going to do the same procedure to each of those 4 squares. So I'm going to take out some plus sign right here. I'm going to take out some plus sign right here. I'm going to take out some plus sign right here, and then right here as well. So I'm always going to be left with, in the setup that I'm doing, with 16 squares. So I think we all see the point. And then with my 16 squares, I'm going to split all of those 16 squares into 4 squares. And then I'm going to have like, oh, I don't know, like 4 to the 3 many squares, which sounds like a lot. Maybe someone can tell me what that number is. And then we just continue this procedure infinitely often. And so what you can prove is that the limiting object K, you take the intersection of all of the Kj that I've constructed in this way. It's called the 4-corner Cantor set, because at each stage, I'm just keeping the 4-corner squares. And you can verify that this set is compact. The set is uncountable, and in particular, it's non-empty. You can verify that it has no isolated points. So you can approach inside the Cantor set, you can approach any other point along points inside of the Cantor set. And you can also verify that it's totally disconnected. These are all the same properties as the middle thirds Cantor set. All the same properties as the middle thirds, 1/3 Cantor set. In fact, they're actually homeomorphic. Any compact set, and there's probably some hypothesis that I have to assume, any compact set that satisfies these properties, compact, uncountable, no isolated points, and totally disconnected, is going to end up being homeomorphic to the middle thirds Cantor set. So all Cantor sets are actually homeomorphic to each other just by satisfying these 4 topological conditions right here. And there's actually some chat in the Discord that they're not necessarily ambiently homeomorphic. So if you go into the topology thread, there is some discussion about this type of thing. So that's maybe an advertisement for checking the Discord regularly. If we're not telling jokes about it, there is actually some interesting mathematics that gets discussed along the way there as well. So this is my 4-corner Cantor set that I wanted to talk about. So what does this have to do with curves? The first thing I want to convince you is that there exists a 4-corner Cantor set, and it has positive Lebesgue measure, planar Lebesgue measure. And this would be analogous to the exercise that I assume that everyone really had to do in Real Analysis 1, where you show that there exists a Cantor set in the line which has positive Lebesgue measure. But it's not too difficult to do this. So I'm going to give a really sketchy proof, and then, you know, I'll leave the details up to all the youngins, all the first and second years. Think about it as comps practice. So what we want to do is basically take out a smaller percentage of area of each square making up Kn at time. So if we go back up to my picture right here, what we're going to want to imagine is going on in mind is like, okay, so we take out some area here when we take out this plus sign. And then we're just going to make sure our plus sign gets really, really thin, and it gets thin fast enough as we keep on going through. So we're going to imagine that, you know, this green plus sign here, this gold plus sign right here is going to be much thinner to the green plus sign here as well. And so what you can arrange, because really only at each stage something is only happening finitely many times, we can arrange for the area of Kn to be equal to 1 minus epsilon n times the area of Kn minus 1. So if you start at Kn minus 1 and I give you some number, epsilon n, that's greater than 0, you can make sure that these plus signs are all tiny enough. You know, there's 4 to the n minus 1 of them. And so you should be able to calculate how much area you would have to remove from each stage right here. So if we have this condition right here, then we can check just using the properties. I think we're just using the outer regularity or something, some limiting property of Lebesgue measure, that the area of K, and area means Lebesgue measure in this case, is going to be equal to the product of 1 minus epsilon n from n equals 1 to infinity. And we can always arrange for this to be bigger than 0. And I think we just need that the sum of the epsilon n's is, well, I don't need to put epsilon n's like that. I think we just need the sum to converge. There's some way to pass through. You want this infinite product to be non-zero if the infinite sum has some sufficiently nice property. So we can construct positive area Cantor sets. And even better, I actually claim that I can run a Jordon curve through this positive area Cantor set. So I want to actually show you how I can take a Jordon curve. So it's going to be a simple closed curve, and it's going to pass through every single point in this positive Lebesgue measure Cantor set. It sounds kind of bizarre, but it's actually not so difficult to do. I'm going to draw a picture at the start. So the unit square is going to be something that we're going to ignore. But the idea is that, well, I'm just going to draw the pictures. So in each square, I'm going to take the top left and top right corner, and I'm going to color them in dark green, like so. And then I'm going to go through all of these squares in some specified order. So we're going to start right here, and then we'll just pass through a couple boundary points like so. And then I'm going to connect these 2 points. So I'm going to connect this lower right-hand point to this upper left-hand point, like so. And then we'll just pass through the rest of the square. So now I'm at this point right here, and I'm going to go up to this third square. So this is like 1, 2, 3, 4. This is going to be the order in which we visit all our squares. So I'm going to connect these 2 points by a hopefully reasonably straight line segment. So we should imagine that these are line segments. And then I'm going to go to the bottom right-hand corner. I'm going to connect with the line segment like so. And then I'm going to go to the bottom left-hand corner. So that's going to be the curve gamma 1. That make enough sense? We're just kind of visiting in sort of this boom, 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 boom manner, like so. Now the Cantor set is self-similar. So when I construct gamma 2, I'm just going to take this construction, I'm going to apply it to each of the smaller pieces in the Cantor set. So how am I going to pass through the stage gamma 2? Well, I'm going to pick I'm just going to do the same picture just at all these smaller scales. So I'm going to pass through here and then go down to this shape. Then we're going to go through here. We're going to go all the way up. Then we're going to go all the way here and then go down and then like so. So we can pass through just by taking this small picture, shrinking it and superimposing it in the upper left-hand corner, passing through in the exact same way. And now the important feature is that because I'm just subdividing the remaining squares at each stage, I can actually keep the same line segment. So the line segment that I chose in gamma 1, I'm just going to fix it in gamma when I fix gamma 2. So I'm just really refining the piece. Every time I break up some of those squares, I refine that portion to get like a new sort of like piecewise linear approximation of my set. And so I'm going to repeat this for the rest of the sets, and hopefully it doesn't take me forever to do so. But I just want to convince you of the picture. We're sort of doing the same thing at every single scale. Boom. Then we go through here. This is sort of the configuration that we have to draw every single time. Boom, boom, boom. All right. Then repeat. We'll have gamma 3 and so on. So here's what I claim. I claim that gamma n converges uniformly to some continuous function gamma from 0, 1 into the plane. That's the first thing that I claim. I claim that the limit function gamma is injective. It needs to be if I want it to be a Jordon curve because it's a simple closed curve. And I also claim that K is a subset of gamma of 0, 1. It's actually not too difficult to verify all of these facts right here. What we have to do is, because we want to show that something's a Jordon curve, I have to build the continuous function. But I'm going to show you how to build the gamma n's, and then we're going to see that it's actually not so bad. So how do we build gamma 1? So I'm going to take this. Oh, I did not want to do that. I'm going to take my picture right here that I just drew. I'm going to copy and paste it and bring it down if it's going to be stubborn like this. I really do hate OneNote. All right. So here's how we're going to parameterize gamma 1. I'm going to take the unit interval 0, 1, and I'm going to break it up into 7 pieces. So 1, 2, 3, 4, 5, 6. And I want these 7 pieces to satisfy. So I have 1, 2, 3. Oh gosh, I can't even count. 1, 2, 3, 4, 5, 6, 7, like so. And I'm going to want intervals 2, 4, and 6 to take up 1/2 of the length of 0, 1. So whatever arbitrary way you want to split these up. All right. So what I'm going to do here is, this is going to be in the interval 2 right here. I have some line segment, and so I can give it some parameterization. So I'm going to parameterize inside of this little interval. I'm going to shade it in. So that's going to correspond to be the parameterization of this line segment right here. And then right inside of here, so this line segment, we'll label it with 4 according to the interval that it belongs in. We're going to parameterize that as some, just linear. It's a line. We can just map it onto itself by doing some stretch. It's a linear mapping, an affine mapping. And then for this line segment right here, that's going to go into 6, right? So we're going to parameterize inside of this piece. So this gives me some continuous function. Well, I've only defined it on several pieces. And then I guess we can just define, going from this point to the other point inside of 1, 3, 5, and 7. That's just the behavior that takes us inside of the square from each line to itself. All right, so that's how I'm going to define gamma 1. Are there any questions about that? I'm really just taking the 3 line segments and I'm just giving them piecewise parameterizations. In fact, we could probably work out formulas if we were really persistent, but I am not. Here's what I'm going to do at stage 2. We have 4 remaining intervals, and what I'm going to do is I'm going to split them all into 7 line segments. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And just like before, I'm going to want so we have 1, 2, 3. I'm going to want those 3 intervals corresponding inside of each of these smaller pictures. I want them to take up half of the remaining length at each stage. So I'm just going to talk this through instead of writing it. And then what I'm going to do, and hopefully we kind of see from the coding going on right here. So we have the little guys, 1, 2, 3, and 4 that we visit. Then we get 3 just linear line segments. So we're going to map this one to the first line segment. We're going to map this one to this line segment. And then we're going to map this one to that line segment right there. And then since we're keeping inside of gamma 2, since we're keeping this line segment, I just keep whatever is going on inside of the second interval right here. I just keep that fixed. This line segment is the same as before. And we do this inside of the rest of the 4 line segments. So I parameterize all the little line segments that I drew to connect myself to the squares just as straight lines. And I'm doing it in such a way that I've taken up after the second stage 3/4 of the area. I've taken half of the unit interval and then I've taken half of all the remaining ones. So does everyone kind of see the picture of what's going on? Because what's going to continue is I'm just going to take every single remaining piece, 1, 2, 3, 4, 5, 6, and then I'm going to take all those small slivers. They're going to take up half the remaining area, and then they're going to correspond to, you know, the line segments that go through each of these subdivided squares. But this goes beyond my ability to draw anything. So that's how I'm going to define all of my gamma n's. All right. So first, we want to address the fact that gamma n converges to some limiting function gamma. And this is actually easy because on a set of eventually full measure and on an open and dense set, the function it's always the same. It doesn't change after some stage, right? Like on this interval 2 right here, gamma 1 is the same on this interval, gamma 2 is the same on that interval, right? All of the intervals are eventually fixed at each stage. So it's pretty easy to verify that gamma n converges to gamma on an open, dense subset of 0, 1. This fact corresponds to the fact that I'm just fixing these line segments. Once those line segments are drawn, I never change them in any of the future functions. And so we know that if I had a continuous function on an open, dense subset, this determines the function on all of 0, 1. So this determines gamma on all of 0, 1. Good. So we know that this is a curve that passes through my 4-corner Cantor set. So the curve has positive area. But like I said, we have these space filling curves and those are not injective. So we're not super impressed yet. But then we have to show that, well, gamma is actually injective. This is a geometric argument right here, and hopefully I can convince you that it's true. But if I take any 2 points inside of my Cantor set, eventually they're going to belong in some stage n, they're going to belong to different squares because they're different points. But this means that in my corresponding interval, those points are going to be separated by intervals that are going to be parameterized by piecewise straight lines. So my function, I can't possibly, it would violate continuity to have these 2 points mapped to the same one. So just sort of using the geometric picture, like the way that we parameterize these segments is done in such a way that guarantees that the image is actually injective at every single stage. So you can sort of pass this geometric argument to where these points belong in the segments. They have to be some fixed distance apart. If there's some fixed distance apart inside of Kn at some points, they have to be some fixed distance apart in the interval, just given the way that we parameterize the space in the first place. I'll leave the details to you guys, but I think it's sort of just a staring at the picture situation. So we have a check right there. And then we just have to verify that K is a subset of gamma of 0, 1. But this is also not so bad because if I take any single point in my Cantor set, it's going to belong to some square in each Kn. And so that means it's going to be the limit of these endpoints that my line passes through every single time in the square. And because the function is continuous, then these points accumulate on the other. I'm going to be able to find some points in the domain that actually map onto that point as well. So the points that are going to map onto the Cantor set are the points that are in this non-open dense subset where we define the gamma n's in the first place. So just by continuity, we're eventually going to pass through the entire Cantor set as well. So this is how you run a pot. This is how you can construct a Jordon curve because it's the image of an injective image of the unit line that has positive Lebesgue measure in sort of this horrible schematic way. And that took up a lot of time. So are there any questions about the construction that we did? Maybe that's the only detailed argument that we'll do, and then we'll kind of talk about everything else a little more casually. All right, good. So whenever we deal with Jordon curves in analysis, like they might be a Jordon curve like this. We can really not give them any reasonable properties. Like we're not going to be able to zoom in at any points and see that it locally looks flat or anything like this. So it's quite a pain. Let's talk about spirals now. This is another Jordon curve behavior that's horrible. So what I can do right here, and I can define some function from -1 to 1, right? There's no reason that we have to fix the unit interval when we define a curve. So it goes from gamma from -1 to 1 to the complex plane. And we're going to use the exponentials right here to define this to the left of 0 and to the right of 0. And so I think what's going to happen here is that when t goes from -1 to 0, we're going to have gamma t is just going to be a spiral that goes counterclockwise around the origin. And then right here, I put a minus I in right here. So this is counterclockwise rotation around the origin. The origin. And then the bottom curve right here is going to go clockwise around the origin. And then we will indeed decide that t of 0 should be 0. And so if you want a little picture of this, I don't know how I found this. I guess it's some like solenoid type picture or something on the internet. It's like maybe it's in some electrical engineering textbook. But what we're really looking at is gamma t can sort of be approximated right here. So we have one point going on the left, and it's going to be going around, well, counterclockwise or clockwise. I don't really know. So it's going to be going around and around and around. And then I'll choose a different color right here. And then there's going to be something going around and around and around in the other direction, like so. So gamma t is a Jordon curve, and it has an infinite spiral around every single point. So as you go around and around and around, it keeps winding. So the winding number goes up to infinity, or the change in the argument goes up to infinity. But if you go from the other direction, it's going to go around in the other way. So the winding number goes down to -infinity, like so. So this is a horrible example that can happen of an infinite spiral. And in fact, you can also guarantee that gamma of t has finite length. So I can construct a Jordon curve that goes around infinitely many of these points like so, that has finite length. So that's pretty bad, but I can actually do much worse than this sort of behavior. Maybe you're like, okay, Jack, that's just one point that we're spiraling around, but around all the other points, the picture actually looks quite reasonable. Well, let me try to convince you that I can do much worse. So here I'm going to draw like some stage of a spiral, and then I'm going to draw some stage of the spiral that comes out. So we go in and then we go out. And then we have 0 right here. So that's going to be lazy, but pretend that it keeps spiraling inside as it goes on. Well, what I can do is I can choose my favorite point on this spiral, and I can erase a little bit of it, like so. And then I can replace that with this spiraling picture. So it goes, oh dear, it's going to go something like, doop, something like so. And then I can keep on iterating this construction. So maybe I can guarantee that this spiral has length 1. And then the second spiral I had has length 1/2. And then you just keep on choosing points, and you keep on replacing it by spirals. And what you can actually achieve is that you can achieve a Jordon curve that's rectifiable and has a dense set of infinite spirals. Just by being careful with this type of construction, taking out a little piece, replacing it by a spiral, and then taking more pieces. So you shrink the length, geometrically every single time. So you're going to have finite length. But if you take any open ball that surrounds any point inside of this infinite spiral, you're going to see some portion, maybe it's really, really small, that spirals around some point infinitely often in both directions. So you can't really assume, this is sort of like some wild, extremely non-differential behavior that's going on, and it can happen just about everywhere inside of the Jordon curve. So again, this is a Jordon curve, and I guess I just connect the endpoints at the end of the day, so that instead of like a Jordon arc, it's a Jordon curve. And you can have a dense set of infinite spirals inside of a homeomorphic image of the unit circle. So that's another thing that when you do complex analysis, you have to keep in mind. And these spirals actually show up kind of naturally in analysis. So I kind of want to start convincing you that these things are actually things that we have to worry about. So right here, I don't really want to define what a Julia set is, but I think we've all seen pictures at some point. But in this Julia set, you can actually, if you're really careful, you can check that near any point on the boundary between this black and green region right here, if you zoom in enough, you're going to see, and you can kind of see it like near points like right here, that there's going to be this sort of infinite spiraling behavior, and it's going to be really generic. It's going to be on a dense set of the boundary right here. So these things show up, and so infinite spirals show up in dynamics all the time. Show up in dynamics all the time. And in fact, they're actually ubiquitous in complex analysis. Infinite spirals are actually like one of the 2 modes of behavior that happen on the boundary up to a set of measure 0. So I want to define a couple points just with pictures. So if I have a simply connected domain, or if I just have a Jordon curve, what I can call a point on my Jordon curve. So this is gamma, and I can call this point Z a cone point if there exists a filled in triangle who has one vertex at the point Z that's contained completely inside of the interior complementary component. If this happens, I call it a cone point. And sometimes this is called in complex analysis literature like an interior tangent. So that's a cone point. But I mean, not everything has to be a cone point. So for example, if I have a cusp, something that looks like some cube root of something, this point's on the cusp, and a cusp can form a Jordon curve. And I think actually Karina's avatar, when you do these Zoom meetings, it has the hyperbolic triangle. So each of the endpoints are cusps. And you can verify that, I'll draw the last leg right there. You can verify that these vertices are actually not going to be cone points as well. So not everything has to be a cone point. And I'll call one of these points where we spiral around and we have winding number that goes off to infinity, and we have winding number around in the other direction that goes to negative infinity. Any point on the boundary of such a Jordon curve is something that I'm going to call a twist point. And it makes sense. You're twisting this way and then you twist that way. It's an old theorem of Mcmillan in complex analysis. It's called Mcmillan's twist point theorem. So my first year at Stony Brook, I learned about this theorem because I took Chris Bishop's class and it was way too difficult for me. But this is always one result that I always remember. So if gamma is a Jordon curve, then gamma, it's equal to the set of all cone points, the sets where I have this interior nice cone, with the union of twist points, points with infinite spirals, and with the union of a negligible set of harmonic measure 0. So I don't really want to talk too much about what harmonic measure is, but it's always worth mentioning. I'm a complex analyst, so I have to give it some plug. So you take some subset of a boundary of a Jordon curve, or really any region, and you start at some point Z. The harmonic measure at Z is the probability, a Brownian motion traveler. So, he can't decide which way to go. He had too much to drink at the cocktail party or something, right? Boom. It's the probability that he exits at this sort of region. So if you have harmonic measure 0, it means you have 0 probability of exiting this point. So maybe we can convince ourselves that harmonic measure 0 is very much a smallness property on the boundary of some Jordon region. But what the twist point theorem says is that if you're up to a set of measure 0, if you're not a cone point, you are a twist point. So you either have this nice cone, or you have the curve winding around you in both directions infinitely often. And you can actually construct examples of curves. I wasn't able to find one, unfortunately, where the cone points have 0 harmonic measure, so that you can have a Jordon domain so that the twist points have full harmonic measure in this sort of sense, so that the twist points can be a really big set inside of your Jordon curve. And so these are just considerations that are going to happen in complex analysis. You either have a nice cone point or you have a horrible twist point, and then a negligible set after that. Tim, do you have a question?
Ken.
Yeah. Oh, sorry.
Sorry, go ahead.
Philip, go ahead.
I was just going to ask, harmonic measure, is that weaker than capacity 0, like logarithmic capacity?
I don't know what the capacity of this set is, actually. I think in general, I don't think it has to have 0 capacity, but I don't want to actually give an answer because I'm worried I'll give you the wrong answer. So maybe we can talk about it in the Discord and I can find the careful statement of that later.
Because I got a little confused about here, because I thought that if you had harmonic measure 0, then you would have logarithmic measure, logarithmic capacity 0. but then I also know that any Jordon curve can contain points of, like it can contain like it has no non-polar parts.
Yeah, I would want to. I kind of want to punt this question off so I can figure out the answer. It's somewhere in Garnett and Marshall's book, but I know, like, for example, that these sets of zero logarithmic capacity, they're not seen by harmonic measure, but I forget how the converse works. But maybe we can address this a little bit later.
Okay. Yeah.
That's outside the scope of things that I remember from my first year. But it's a good question. I mean, how capacity relates to this is interesting as well. Tim, did you have a question?
Yeah, I'm thinking that probably N could have positive Lebesgue measure, though. Is that correct?
Probably. It could have maybe big Hausdorff dimension or something like this. Probably, that's probably true. Like I said, I'm not too careful about these points. I'm kind of just doing more of an advertisement, being like, oh, you got twist points or you have cone points. But yeah, I mean, harmonic measure doesn't have to be the exact same thing as Lebesgue measure, I think.
Right.
I'm going to get into trouble if I keep saying this. I think this talk was online, so.
You know, as curves embedded in the plane, Lebesgue measure is not necessarily the natural place to look.
Exactly,
anyway.
yeah. So at some point, I agree with you. It probably can have large dimension.
Okay.
And that's why it might not have zero capacity, right? Because a set of zero logarithmic capacity always has Hausdorff dimension 0. There, I said something intelligent. So we can talk about it later in the Discord. But yeah, that's the twist point theorem. So, you know, infinite spirals are something that complex analysts have to live with. So I really only have like 5 more minutes. I wanted to talk about the lakes of Wada, but maybe I will talk about the theorem that I proved, since I want to talk about what I proved and brag a little bit. So I want to return to our algorithm, maybe now that I've convinced you that Jordon curves can be these really horrible objects, and sort of address Sam's point that maybe you just can't cross a Jordon curve in a nice enough way for this algorithm to work in general. And so this is actually a theorem of my advisor, Chris Bishop. In 2010 or something, someone just asked him to make a counterexample, and this is what my advisor does. He builds counterexamples, and he shows that there exists a Jordon curve so that if sigma is any line segment crossing gamma, so it has a point in the interior and a point in the exterior, then sigma cap gamma is always uncountable. In particular, you cannot cross the Jordon curve, go from the inside to the outside by a line segment and pass through at a single point. You have to pass through uncountably many points. I'll draw a picture of what these things look like. But in particular, those who know what Hausdorff dimension is, you can actually guarantee that the Hausdorff dimension is 1, but not necessarily positive H1 measure, not necessarily positive length. The proof of such a horrible Jordon curve, what Chris does is he sort of studies these curves that are just the union of semicircular arcs. And then he shows how to refine them in such a way where you get this sort of crescent formation. So if you start with one of these arcs, then you subdivide with all these points, then you get these crescents right here. And then you, near the tip of the crescent, you draw these little balls. And then what eventually ends up happening is that you get a new curve. So you start with some base curve gamma, and you can construct a new curve which wiggles along these crescents that we formed according to these pictures. And then the way the proof is gonna work is that at some stage, so I can like thicken the neighborhood of this line right here, if a line segment crosses the set, it has to pass through sort of one of these situations, a tube, and then all of the crescents inside of that tube in the construction. And the way that the crescents are defined is that they're loopy enough so that any line segment has to cross any of these. So basically, if you draw this picture and then replace every single point by a suitably scaled down portion of these crescents, you can construct a Jordon curve where you cannot cross at a single point with any line segment whatsoever. So this shows that our algorithm for proving the Jordon curve theorem, it will not extend outside of the polygonal case. But maybe I can take a detour, right? Like maybe I don't have to be as careful as a line segment. Maybe I can do some sort of like piecewise linear construction or just some sort of finite length construction that I only pass at finitely many points. Well, that also doesn't have to be true as well. So it's a theorem of Charles Pugh and Conan Wu that there exists a Jordon curve so that if sigma is any rectifiable arc crossing gamma, so here's my Jordon curve, and sigma is just going to be some finite length arc, and it can take as many detours, it doesn't have to be a bunch of polygonal segments, then sigma intersects gamma at an uncountable set of points. It cannot cross, no rectifiable arc, no finite length arc can cross the Jordon curve at one point. It always has to be uncountable. And interestingly enough, I want to show you maybe pictures of what these curves look like as well. Interestingly enough, Jordon curves with this property show up in differential equations. So they show up as the solution funnel. So if you have a ODE and it has an initial condition, then you don't necessarily have to have a unique solution. So I guess we can view these things as vector fields somehow. I'm exposing myself for not knowing enough ODE. But if you have a non-unique solution, you have a bunch of trajectories going through this point. And that's called the solution funnel. So it's going to be large. There's multiple solutions, and you can take cross sections of the solution funnel like so. So right here, I have a point, bunch of solutions go through there, and you get some compact set inside of Euclidean space when you consider the solution funnel. So what Pugh and Wu show is that Jordon curves with this property show up as the solution funnels of ordinary differential equations. So they show up as the result of bad behavior and some differentiable process. So that's really interesting that it has connections to differential equations in this sort of way. And I kind of want to show you how they construct the curves. So what they do is they call this a button curve. And so it goes back and forth like so. So you can sort of like wrap this around. And then they replace it with a zipper. And they somehow make this all related to differential equations so that they can prove this funnel section result. But if you go from one side to the other side of this curve, they rig it so that you have to go through a zipper at this stage. And so the length has to keep on getting longer and longer, and they keep replacing things by zippers so that no finite length thing can cross this. So it's a pretty fun result, and there's lots of good pictures. It's actually a really wonderful paper. All right, so this kind of made my advisor ask me this summer. He wanted me to prove a paper so that people would make a proof so that people would want to give me a job. And so with this property of Pugh and Wu, they don't address, what's the Hausdorff dimension, like what's the biggest size of the crossing beyond uncountable? Could it have positive length? And that's actually the theorem that I proved recently. I show that there exists a Jordon curve gamma so that if sigma, it's a simple rectifiable curve that goes from the interior to the exterior, then the length of sigma intersected with the Jordon curve that is crossing for any rectifiable curve, it's positive. It's strictly bigger than 0. So not only is it uncountable, it's a set of positive length. That's as big as the crossing can possibly be. So what do I mean about the length of the intersection? What I mean is, for those that know that what the Hausdorff 1 measure is, or what you can do, since it's a simple curve, you can pull back the parameterization since it's finite length, and you have Lebesgue measure inside of there. So you can take Lebesgue measure of the set of all points that land on the intersection of the curve and the Jordon curve, and you can verify that that's positive every single time. So it crosses the curve on a meaningful Lebesgue measure set. And I claim that this result is sharp, but maybe I can address that to people afterwards because I think I'm at my time right now. But I kind of want to show you some pictures that show how the curve gets constructed. You play like this fun game of snake, basically. So what you do is you start with some rectangular tubes, and then you create more tubes inside of there that sort of snake back and forth. So it's like you've been playing snake for several hours, and you just have to keep going back and forth and back and forth and back and forth if you want to not lose. And so what this means is that the only way to cross from one side to the other of this Jordon curve, if I only want to cross at one point, I have to go through these little channels every single time. But the channels are spaced out in such a way that it costs me some amount of horizontal length to go through them. Right? If I want to go down this nice little horizontal channel, I have to go in this left or right. And so the way that the proof works basically is that I rig this setup so that if you want to pass through one of these channels, you have to pay a toll of some amount of length. And what I'm able to show is that that toll goes up too high as you keep on going through this construction as you go through and through. There's just way too much time spent being horizontal relative to going vertical. And that wastes too much length. So you cannot possibly cross at one point doing a finite length thing just because this horizontal distance covered cannot be crossed. And so, I don't know, I have a bunch of pictures I can show, and I'm sorry for going over time, but this is, again, how the construction works. You sort of take a rectangle, and then you create some new tubes, and it goes through, and you continue to do this at each stage. And it gets very bad very quickly. So you have something that looks a lot like this, going through and through and through and through. So we see how our horizontal distance that we're traversing every single time is much larger compared to the vertical distance. and it's simply too much for a rectifiable curve to cross at exactly 1 point. I can show that it has to cross on a set of positive length. I think since it's 102, I'll conclude on there. I can talk a little bit more afterwards, or I can address some questions, but yeah, that's all I'll say for now. Thank you.
Good talk. Thanks very much, Jack.
Yeah, thanks.
Any questions?
Anyone?
Could you just go back up to the statement of your theorem? Because I didn't quite.
Yeah, sorry, I was rushing through it a little bit, yeah. So yeah, if you have any, I don't need to even include the simple rectifiable curve in there, but any rectifiable arc that crosses gamma, its intersection has positive Hausdorff 1 measure. It has positive length. So like the crossing set, like the intersection set, it contains a positive area Cantor set, or which lies on the line. That's kind of an alternative way to view it.
Okay, yeah, I got it. Thanks.
It's the worst possible because finite length curves, if I am allowed to have infinite length curves, well then since it's a Jordon curve, I have the Riemann mapping theorem, and that says I can map the disk to the interior of that, and I can map the exterior disk to the exterior of that. But then I have the hyperbolic geodesics in the disk, and those are going to get mapped to the geodesics in this object. And they're going to have infinite length if they want to cross it, but they're going to be analytic almost everywhere, except on the boundary point that it touches, because the map extends to the boundary of the circle by Kara-Theodori. So you can always cross at 1 point with extremely smooth objects, except at 1 point. You know, they might meet in a horrible way. So you really can't upgrade the finite length to anything meaningful. It's about the worst it can possibly be by the Riemann mapping theorem.
Could I ask a question?
Oh, of course, Ben.
Yeah, great talk, Jack, by the way.
Oh, thanks.
It's not really about the theorem, but I was wondering, are there any analogs of these Jordon curves in higher dimensions?
So just like any of these examples
like in
that
3D, like can you separate? Is there like if you have a surface or something? Is there always?
Yeah, that's pretty
interior,
interesting.
Exterior.
I don't really know, to be honest. So I think once you go up into surface world, curves are just much nicer. Curves in the plane are really nice, and Chris just said this in his class, because they have dimension 1, at least topologically, they're images of lines, and they have codimension 1 as well. And whenever you upgrade into a bigger situation, you never have that relationship whatsoever. So I don't know about any interesting results about surfaces. I don't even really know how to state them necessarily, but
yeah, makes
sense.
sense.
You can do some pretty awful things. I talked to Fred once about varieties or something. If you have an algebraic variety, I think I'll just say affine algebraic variety. I'll stay in my lane a little bit, but that's going to be nowhere dense, I think, right? Like this is how the Zariski topology is defined. But Fred was telling me once about some sort of quantitative nowhere dense thing where maybe, okay, it's nowhere dense, but everything is still reasonably close to each other, and you can have some pretty horrible windy situations. And he was trying to convince me that that was related to this, but that's the most my understanding goes.
Okay, thanks.
Yeah, no problem, Ben. Anyone else have any questions?
Yeah, can I ask one more, actually?
Yeah, go ahead.
So when you claimed that this was like the worst possible Jordon curve, that was in terms of this Riemann mapping theorem thing that you just said, or?
Yeah, I claim that you really can't sharpen the results and get a meaningful result of this form. So what I want is I want a class of curves. You can define some class of curves, and I would like them to have to cross on a set of positive length. They have to cross the curve on a set of positive length. So I can't make finite length. I can't improve that to a larger class of curves, because as soon as I allow infinite length, by this Riemann mapping argument, these hyperbolic geodesics, which are analytic except at 1 point, they will cross at 1 point. They're capable of doing that. So I don't think there's like a meaningful larger class of curves to which the conclusion is valid. So that's where I try to justifiably say that it's the world's worst with those that satisfies this hypothesis.
I see. So sorry, is the Jordon curve, is that the one with finite length?
So the Jordon curve is actually
No,
going to
sorry,
have
that doesn't
positive
make sense.
area.
Yeah,
Yeah.
sorry. The sigma is the one with finite length.
Yeah, exactly. So like, for example, if this is my picture, this is some stage of my curve right here, right? The curve is going to be defined in a limiting construction, just like everything in this talk really was. I did have to brush some details under the rug, but if you cross this, then like so, that means the intersection of this with the Jordon curve has positive length. So you can just pull back the measure to an actual unit interval and take the Lebesgue measure there, or do the Hausdorff one measure. So that's positive length.
So if the thing in blue is infinite length, then your result, it can cross in a single point by this Riemann mapping theorem.
Exactly. If I'm allowed
Okay.
by the Riemann mapping theorem, I can do this.
Okay. Okay.
Instead of
Great.
one point if
Yeah,
I
that
have
makes
it.
sense.
Yeah.
Okay. Thanks.
Yeah, of course.
Yeah. Great talk again.
Oh, thank you. Anyone else
This
have any
isn't a
questions?
question. This
go
isn't a
ahead.
question. I'll just mention that Philip put something in the chat which sort of addresses Ben's question about an injection of a n-sphere
Oh, yeah?
separating n+1 space. I don't necessarily need to read off what he says, but
Oh, okay. Good, yeah. All I know is that dealing with fractal spheres is a much worse business than dealing with fractal curves, I guess. I try not to think about it too much. It's a little scary.
great talk, Jack.
Thanks, Tim. I appreciate it. Anyone else have any questions? Cool.
Well, if not, then thanks very much, Jack.
Yeah, thanks very
Great
much,
talk.
everyone. Good to see people. Yeah, thank you.
All right. So today is actually the last talk of the semester. So we're just gonna continue again
encore.
next year. See you guys. Happy holidays. Enjoy the break. Right.
Stay safe, everybody. Be well.
Bye.
Bye.